All right. Okay, so let's talk about the process of deciding how is it that our database is going to be structured. Right? And as we mentioned earlier, the task of deciding, the tables and the fields and their data types and if we're going to have them relate to one another, what foreign keys, primary keys, how they're going to structure that set of tasks is referred to as data definition, okay, or coming up with the data schema of how the structure of a database is going to look like. So let's take a look. So as I mentioned earlier, the central idea of how we're going to break up the our data is in the terms of tables, right? It's a kind of like a grid of data sets, right, where we have vertically we have multiple fields, and horizontally we have multiple rows, right? Where the columns refer to the various attributes of a particular collection of entities or pieces of data that describe a particular instance of something, okay? Whether it's be a course or student or product, and presumably each one of those individual instances, they all have similar or identical properties, right? All products might have a SKU, might have a description, a price, and whatnot. Okay, and just like students might have first names, last names, and whatnot, and student IDs, and each one of these sets of properties is referred to as a row, right, or a record. So it's a record. That's the high level abstraction of what we mean as a small little data set, but it's represented in the table as a row, right, in horizontally. And the columns are the various fields. And each field will have its own data type, saying that certain things are strings, certain things are numbers, certain things are dates, and whatnot. Okay? And these data types are used for the database to validate, right, whenever we are manipulating the data in the data set. Right? They are constraints. We'll see that as we progress through the data definition, we'll introduce the idea of constraints. Right? Is how much do we want the database to allow certain pieces of data and which should it reject, right? Or how we're going to ask the database to help us, right? Make sure that the data that we're putting in there is good data, right? Including whether if we're expecting something to be numbers and we're not putting dates in there or strings or alphanumeric characters. So these constraints. Those are the simplest constraints, right? The data types are the simplest constraints. They could become fairly sophisticated types of constraints, right? Including relationships between various records, right? If you have records that are related to other records, there might be certain constraints. Just like, for instance, if you have a file and you have a folder, there is a relationship between a file and a folder, right? If you can remove a file with no constraints. Well, perhaps depending on your privileges, but typically you could remove a file. But what about removing a folder? Typically, there's a constraint between a folder and files that may be contained in the folder, right? You would not be allowed to remove a folder unless there are no files in there, right? It says you have to first remove the files before removing the folder. So same thing here. The records, if you have records that are somehow related to one another, right? You might be constrained of removing a record that is being referenced by several places, right? That if you remove it, everybody who refers to that original record would be left orphaned, right? That they would be referring to something that doesn't exist anymore. Okay, so that type of constraint we call it referential integrity. Right? We want to make sure that if you have these references, that there are always true references, right? They're not referring to something that doesn't exist or referring to the wrong thing. And so as we progress through the course, we'll talk about all sorts of types of constraints. Again, for the file system to represent some reality, some real phenomenon, some real rules, business rules that we want to validate. So So here's what we refer to, the structure of our data. We refer to it as the schemas, right? And so here we have represented 5 schemas, right, for the student, department, course, sections, and the enroll table. Each one having several set of fields, and just by describing this, the name of the table and the fields, we refer to that as that is the schema. One of the things that is missing from the schema is the data types of each one of the fields, but that, if you would want that detail, you could see what the actual definition of the schema might be, of the table might be. Notice that we have certain things are bold, certain things are italic, and bold fields typically means that they are keys, right? If they're bold and italic, they're probably primary keys, right? A key typically is unique, right? But you might have certain things that are unique. Maybe you might have an email in here, right? Or somebody's LinkedIn URL. That's things that are unique, but we are not using it as an index, or we're not using it to refer to other things, right? We know that they're unique, but they're not the primary key that we use it to relate these records to other records. Okay. We also have lots of real data in here, like student names and graduation year, and the department name, the title of the course, and so on and so forth. Those are real fields that represent real phenomena, right? In some reality. Plus, we have other fields in here that are used for implementing the relationships between the various schemas, such as the department ID and the major IDs, right? And here the student IDs and the section IDs. Those are all foreign keys, right? They are referring to values stored in primary keys of some other schema, right? So this student ID presumably is a value of some SID in the student in the student table, right? And presumably the referential integrity will not let me, for instance, store a value here if the student doesn't exist with that particular ID. Right? So that, again, saving me from implementing relationships that are not true, right, or invalid. Okay. Again, these constraints. That's another constraint, saying that this is not only unique, but it is a primary key, meaning it is going to participate in a relationship. Right? This is not just any field, but it's a foreign key, meaning it's referring to something that exists here, some other primary key. Those are all constraints. Right? Constraints on a database allows us to have the database validate that we are storing the data in a correct fashion. So here's an example of several records referring to one another. You have 2 students, Joe and Dean, of various graduation years. We have the primary keys, SID 11 and 22. Notice that we have the enrollment table referring to them, right? It says that students' IDs 22 and 11 is referring to those records over there, and it's somehow relating them, saying that they are enrolled in these sections 321 and 123 that are down here that have additional information such as the professor and the year offered and whatnot. And the section itself has its own primary keys plus some other foreign keys that are referring to the courses for that section. Saying that section 123 is actually one of many sections for the course 21, whereas section ID 321 over here is one of many sections of the course 32, which is thermodynamics. Okay, right. So all the colored fields are meant to participate or relate the various records amongst each other. Now notice that the data we had decided that we wanted to split it this way. We haven't said why we chose to split it this way. Right? As we go through the data design phase, it will come to the conclusion that this indeed is the best way to break it up, right? And depending on the kinds of questions we wanted to ask originally, right? Although we haven't gone through that, we'll go through several questions, and those questions will guide us to the conclusion that this indeed is the best way that we can represent it. We'll then consider other questions What if you make something plural? What if you add this additional verb, or this additional noun, or this additional description, or this additional question, right? They will have to come back and say, ooh, we need more constraints, right? We need another table, we need another field, we need another foreign key here or there, and we'll come back and modify this. Notice the big old questions. Why do we bother, right, splitting it up into 5 tables? Couldn't we have just had it in one big table, right? Where we have, the students, and just in that one table you can have everything very conveniently. The student name, the graduating year, the department, the title, the professor, everything is one single place. Right? But you notice that a lot of the data here is being captured multiple times, such as chemistry is being there multiple times, calculus, thermodynamics, the professors, the years, right? And that should give us a hint that perhaps this is not the best way of capturing this information, right? That we call this a denormalized representation of the data, right? It's not normalized, right? When you split it, the act of splitting it into multiple tables is called normalizing the data, right? And there's several levels of normalization, right? We'll talk about normalization of normal form 1, 2, 3, and there's a couple others. We'll go all the way up to 3, and each one is going to address certain problems of redundancy. Some of them will be obvious redundancy that we want to fix. Some of them are going to be very subtle, okay, that are not evidence that they're a problem unless you start asking certain questions and say, oh yeah, I don't want to store it that way. I see where the redundancy might be a problem. And we'll talk about that a little later when we talk about normalizing data. Null values. Null values are meant to represent the lack of data. Right? It doesn't mean that a 0 or -1 or empty string. It means that I don't know what it is. Okay? I don't have a value for it. Okay? And so because it's null, you don't know what the value is. It makes no sense to consider its value because there is no value. It cannot participate in any comparison. You can't say it's greater than something or less than something or equal to anything because there is no value. So oftentimes in your queries, you need to make sure that you might be comparing some of those records, those fields that you're using might have null values in there, right? And oftentimes you might have less results than you were expecting. It says, why I only have half of the values I thought of records that I thought there were, right? And probably it's because you're comparing against records or fields that might not have a value and they do not participate in your query. So be careful with the null. It represents the lack of information. Also, when you start inserting data into and creating records in the table, they're naturally stored in a particular order, right? Typically, it is added. Last insert is the last piece of data that was added to the file system, right? Until you start indexing. And one common question is that you might want to use the natural order of how you insert the data. You want to take advantage of this original order. Perhaps you insert it in there in a particular way, right? Or there is a skewed mechanism by which you're inserting the data already alphabetized or already ordered by some natural index, right? Now, even though there is a natural order, you should not. The actual order is not guaranteed, right? You should never rely, right, on the actual order of the records that are in the database, right? The database is free to return the data to you in any order it wants, unless you specify a particular sort order, right? You should think of it as a collection, right? As a data set, right? Where there is no first or second record, right? There's no first elements, right? They're all equally the first. They're all equally the last, okay? You would only consider sorting if it's for human consumption, right? If somebody wants to consume the data, they might want to see it in a particular order, right? But as data goes, it really there's no value in choosing one order versus another. right? It's only for the way the human wants to consume it, and perhaps for optimizing the retrieval for the most common way that you want to retrieve that data. Of a record. Oh yeah. So typically what we do is that to specify or talk about any order, right? It's usually based on the related to a particular field, right? The order only means when it has any meaning when you talk about a particular field, right? Is it ordered by last name, or is it ordered by phone number? Is it ordered by what? Right? Once you choose the field, then you can talk about any particular ordering. Also, we want to guarantee that, again, that data is not redundant, that there is no replication of the data anywhere, and we want to somehow guarantee this, usually by choosing some field and guaranteeing that it's unique, right? Some fields might seem to be unique, perhaps a last name. Again, within the context of this class, perhaps our last names are unique, right? But typically, we cannot guarantee it across an arbitrary large context. So typically, we think of some field as uniquely identifying the record. Now, a super key is either an individual field or a collection of fields that together uniquely identify that particular record, right? Perhaps your first name and last name make you more unique in this context, right? Or maybe your first name, last name, and your middle initial, or your first name, last name, and wherever you live, or your phone number, or something, which makes you even more unique. Now, if you are unique enough, right, that if you keep adding more fields, don't make you any more unique, right? Those additional fields, right, that you were trying to use to make you more unique are considered to be superfluous, right? They don't make you any more unique, right? So the minimal set of fields, the minimal set of fields that make you unique is what we refer to as a key, the key, right? The minimal set of fields that make that record unique. Okay. Oftentimes it's just one field, right? For instance, a social security number. Right? That's enough. That's enough to make me unique in this country, right? Again, always within some context, right? So my social security plus my name doesn't make me more unique, right? My phone, social security number plus my phone number doesn't make me more unique. Maybe my phone number makes me unique. Maybe my email makes me unique. Any one of them could be a key, right? Typically, some of these keys are arbitrarily selected, or we can also choose a combination of fields make me unique. Okay? The fields. The fields should always be considered on what the intention of the field is, right? Ideally, you could use a real field, right? Some real data to make you unique, such as an email, right? An email does represent something, some piece of data from reality, right? So, and typically, oftentimes, it's used as a unique key identifier for in some data sets, right? More often, because we want to make sure and guarantee. Oftentimes these keys are arbitrarily chosen, like your NUID. Right? It's arbitrarily random, right, and arbitrarily unique within the context of the university. Right? Most cases it's just some arbitrary value. Right. So the keys. A key should never be selected just because you've looked at the data and by inspection it looks like it's unique, right? It might be a field that you're not familiar with, right? Perhaps because it's some domain that you're not familiar with. Maybe you're trying to represent, I don't know, some physics or chemical domain or some domain that you're not familiar with. Okay. and you look at all these fields of this record, and you don't know what this field means, right? And you look at the data, and you inspect it, and it says, oh, well, they don't repeat. It looks like it's unique. I'll choose that as my key. Okay, that should never be your strategy, especially if you don't know what the intent of what that field is. If you know that the intent is that that particular field will never ever repeat, then it makes sense for you to choose it as a key, right? If you once understand what the intent of the field is, yes, but never from the content, right? It would be as looking at this class and nobody has the same last name, and then reasoning saying that, oh, last name is a good field to use as a primary key, right? You would be wrong, right? You know, maybe within this context you might be right, but it would definitely not be guaranteed as in a more general context. Make sense? Yes. So it's always the intent of the field. Also, when you choose a combination of fields, notice that you can take the combination as a constraint on the records that you're going to insert, that you're going to allow to insert. Okay. So, for instance, if you say that your key contains the combination of student ID and section ID, then you're saying that, and that needs to be unique, meaning that no other record can have that same combination, right? That you cannot be enrolled, that a student cannot be enrolled in the same section more than once, right? Because it's unique. So that kind of constraint can be used to implement business rules, right? So if somebody says, you can only have one car, right? Perhaps then your primary key can be a combination of the license plate plus a student ID, right? So that combination makes it unique. So there's no way that you could have more than one. So if you take different keys, like a combination of professor and year offered, or course ID and year offered, or course ID, professor and year offered, these introduces different constraints on the data that you would allow to insert into the section table. So for instance, if you have the key of combination between professor and year offer, you're saying that the professor can only teach that course once a year, right? Because if you try to insert the same professor the same year, maybe in a teaching something else, right? Then we would not allow to insert that record, right? Because it would violate the uniqueness constraint, right? So depending on these rules, right? Somebody might give you these rules in spoken English, right? You would deduce, right? This would deduce, or what would be the constraint in the database, right? That would enforce your business rules. Make sense? Right? Typically, you read through a passage, right? You read through the requirements in the requirements phase of a project, right? You start creating your tables and your fields, right? And you start identifying your primary keys, and you start creating these constraints, to enforce these business rules. Here's another one. A course, when you have the combination of course ID and year offer, it means the course can have at most one section per year, right? Or that a professor teaches at most one section of a given course per year, right? So again, the trick is that you would be able to implement business rules here. So here's a couple of records that would violate the three rules that we just mentioned. For instance, the first one we have Professor 123 inserted twice here, and even though that professor is teaching different courses, different sections, right? This one is violating the first constraint, right? Because it's the same professor, the same year, but this professor would be disallowed to do that. Over here, we have a combination of course ID and year offered. Even though it's two different sections, which would be okay, I should be able to teach two different sections of the same course. Because of that rule, I'm not allowed. Same year, I cannot teach more than one course. One section of the same course. Over here, we have the combination of years, professor and course, I would be breaking the third rule listed here. Now, duplicate records, by default, databases don't enforce, don't disallow duplicate records by default. So you could very well insert records all you want with duplicate values, right? You have 1, 2, 3, 4 records with exactly the same value, right? Now, and by default, the database won't stop you. Okay. Now, if you try to do that, there's no way for the database to distinguish one record from the other, right? Because any operation that you want to operate on any one of these records, you're going to have to be able to somehow tell or identify which record do you mean, right? And it will typically be by giving it some kind of predicate. Oh, it's the record whose year is 2017, right? And but wait a minute, all the records have 2017. And they say, okay, well, no, it's 2017, and the professor is 1, 2, 3. Well, no. All records have 2017 and the same professor. So it doesn't help me. Which one do you mean? So there's no way to distinguish any of the records. So any am I screaming? I think it's screaming. So any record that you try to refer to, right? Any action, right, will be applied to be equally to all the records that you're trying to refer to, right? Regardless of what, how unique you want to try and refer to any one record. So the database is not going to help you. You have to specifically ask the database to please mark certain fields to be unique, right? And one of the ways is to use keywords such as unique, right? You can say this field is unique. For instance, if it's a phone number, if it's an email, if it's and you know that it's going to be a unique field, you could tag it as unique, and that would fix it, right? That would fix it and guarantee that you would not be allowed to insert a record that had the same value. Now, and that would help. That would go a long way. Now, additionally, you could say, well, no, this field is unique, and right, it's participating in a relationship with some other records in the table. So you would have to explain to the database that indeed it is going to participate in this kind of relationship, and I want you to validate and make sure that the referential integrity, that I can remove one if I haven't removed the other, and things like that. I don't want any orphan records, right? And you would have to additionally tell it that it's not only unique, right, but it's a primary key, right? That it's a unique value, but it's also primary, meaning, hey, additionally, make sure to enforce constraints. So primary keys is for participating in relationship. Ideally, these keys would be some intuitive, real field, such as an email, right, or some combination of fields that make it unique. Oftentimes, they're just plain old artificial, right? Just some random number that is guaranteed to be unique. Oftentimes, it makes sense to just let the database choose, right? Hey, database, you handle that. You choose some unique value for this record, either by a counter, right? That would start at 1, and then it would just increment every time you insert a new record, 1, 2, 3, 4, and so on and so forth, or from a sequence, a predetermined sequence. In some databases, use that mechanism as well. And foreign keys would be fields that are going to be referring to the primary key, right? And that once you tag, they don't have to be unique, right? Because you could have multiple records referring to the same field, right? So, for instance, multiple people working in the same department, right? Where you have one single department, but multiple folks referring to the same department that they work at, or multiple students enrolled in the same course in the same section. So foreign keys don't need to be unique, but they are referring to something that is unique, right? They're referencing something that is unique. And once you've tagged these fields to be primary and foreign key, the database will enforce certain rules when you create records or try to remove records. So here we have several fields that are foreign keys in these various tables. Like the major ID is a foreign key referring to the department. Department ID is, in course, is referring to the department, and so on and so forth. We have course ID, student ID referring to their respective tables. And this is the nomenclature that we're going to be using throughout the semester in our schemas. We have the table name in all caps using underscore for multiple words. We have the non-keys are not bolded, right? They're in simple text. If they're keys, then they are bolded, such as bolded and italic, such as primary key and foreign key here, like SID, department ID, course ID. If they're underscored, they are primary keys, right, referring to a foreign key. I'm sorry. The foreign keys, right, referring to their primary keys. Okay. All right. So yeah. So this is the schema of the database. One of the nice things in a relational database is that the keys, primary and foreign keys, when establish a duality of direction between the records, right? With the you're given a record that has a foreign key, you can navigate. You have a reference to the record that you're referring to, right? So you can navigate. Right, giving a record, you can, with a foreign key, you can navigate to the original record that you were referring to, and vice versa. Given a record, you can find out all the records that are referring to you. So you can navigate both ways, right? From children to the parents, and from parents to the children, right? Unlike you would, for instance, in Java or C++. Typically, in these object-oriented programming languages, the relationships typically go from the parents to the children. It is the parents who have references to the children, perhaps using arrays or collections or lists, right? You might, for instance, a department might contain an array of courses, right? Or a list of courses, or a set of courses, or a map or hash table of courses. Typically, the courses won't have references back to the department, right? It's a very uncommon to have children, right, refer back to their parents, right? It is the parents who have references to the children. Also, notice that so typically you could, right? You could have children having pointers back to the parents, and you can have both directions, but it's less common. It's less common to do that, right? To data model it that way. Also notice that the way we model the relationships is completely backwards the way we do it in relational databases as we do it in programming languages, right? Notice that in relational databases, it is typically the children who refer to the parents, right? It is, for instance, all the students referring to the departments. All the students have a reference back to the department they belong to, right? They have a foreign key back to the primary key of the department. Yes? But that's not typically how you would model it in Java. Typically, you would have the departments, right, having references to the children. See that? It's kind of backwards, right? And that's one of the challenges that we're going to find later on, right? When we try to map these two worlds together, we try to bridge these two worlds. It's that oftentimes referred to as the impedance problem, right? The impedance problem is it's a collection of challenges of trying to map one data representation with another data representation, even though we are capturing and referring to exactly the same piece of information. Right, the way you represent it in one world cannot be uniquely represented in the other world. Right, Java has its own data types. Oftentimes not, they don't have an equivalent or analogous representation in SQL, right? And you have all sorts of things in object-oriented you can't even do in relational database. So anyway, we'll get back to that a little later. Yeah, so it works in both ways. Given a department, you get all the students, or given a student, you can get the department. Referential integrity, it's enforced, making sure that if you're trying to manipulate the children, that you don't want to leave them orphans, right? So if you try to remove a department, if there are any courses or that are tied to that department, I cannot remove the department unless I remove the courses as well. Okay? Or if I try to change the primary key of the department, it won't let me because I have a whole bunch of other records referring to that department. Okay? Also, I might configure the database in such a way that naturally, if I remove certain things, I want to also remove all the children, right? In some cases, that might make sense. For instance, if you have records that represent a website that contains lots of pages, that contains lots of widgets, right? If you remove a page, maybe makes sense that you might remove all the content in that page as well, all the records that contain the content of that page. That makes sense. And if you remove the website, then it might make sense that you would also remove all the pages in that website, and you remove all the widgets in those. So you kind of like cascade the entire delete, right? You remove the top level parent, and you can cascade the deletes all the way down to all the children, right? In some places it makes sense. But what about if you have departments, you have students registered in the university? Say a department goes away. Do you also remove the students? Well, I don't know. It might make sense. It might make not sense, right? Might make more sense perhaps to move those students to a different department, maybe, right? As opposed to just removing them, right? So those business rules, drive us to implement one particular implementation versus another implementation. What to do with how to handle the removals of parents versus children. So here's an example. We're going to try and remove the math department, and you have two students who are majoring in the math department. What happens? If I remove the department, do I cascade and remove the students? If I change the department ID, what happens to those that are referencing this, right? So typically, referential integrity, by default, won't let you do anything. It says, no, you can't touch that. You cannot, I have folks that are referring to you. I can't let you manipulate this unless you remove these relationships first, okay? Or you can be a little more explicit and say, well, no, if this changes, then all these others are going to change as well. If I remove this, these are also removed. By default, I cannot remove because I have these folks referring to them, right? And that's all those ideas are referred to as enforcing referential integrity. Okay, and you can have all sorts of cascading actions, right? That if you delete one, if you delete the enrollment, right, cascades and deletes all the ones there. Or if you really remove a student, then it makes no sense to keep track of all the enrollments that student was in, right? But typically you would not cascade and delete all the sections, right? Because you might have other students in that section that you don't want to remove. Okay, so you can configure what it is that you want to happen. How do you want to cascade those changes? Whether you want to update those values, right? If it changes, I want to also update the value of the other one. Or if I remove it, I want to remove the other one, right? Other constraints, I might make certain fields. I might make certain fields required fields, meaning that if you don't give me the email, I won't let you register. That makes sense, right? Or if you don't give me a password, I won't let you register. I need that, right? So certain fields might be optional, some fields might be non-optional. So I could say that certain fields cannot be null, right? So I won't let you insert key constraints. We've looked at that, referential integrity as well. And so constraints in general enlist the help of the database to validate the database. So all these actions of creating the schemas, of setting up these constraints, the data types, and the relationships, and the primary keys, they're all encapsulated in a in a pseudo English kind of language referred to as the structured query language or SQL. That is, the de facto standard by which we interact with databases. To create a table, there's a command for that, create table, that allows you to give it a name, list all the fields, the data types, and all the different constraints for that schema. Here's an example of using SQL to create the student table, saying that we're creating all the fields, SID, SName, major ID, and graduation year. So these are the 4 real fields, right, that are going to capture data. Well, actually, no, there's really 2. The SName and graduation year are the only ones who are capturing real data. The other 2, SID and major ID, they're only because we're splitting it up. We're splitting up the data across multiple tables. And these will allow us later on to reconstruct, right, the data that we've split up into one single piece of data. We have data types for these. That this is a string of 10 characters. There's an integer, and it's required. It cannot be null. The name also cannot be null. The major ID and graduation year are optional. We don't have not null in there, so it's okay if we don't have values for those 2. And here are referential integrity constraints saying that the SID field over here is a key, and it's the primary key. So it's unique, and it's going to participate in relationships. Somebody is going to refer to the SID, right? Such as the enrollment table, right? The section table is going to refer to this. And records here, values for the major ID in this field are going to be referencing the primary key of some other primary key in some other table, right? In the department table. And if that department is removed, right? If it's removed, then the value of the major ID is going to be set to null, right? And if the value of the primary key in the department changes from 20 to 21 to from 30 to 34, whatever, right? The primary key, I'm going to cascade update, meaning that the value is also going to change here as well. So any children that are referring to that department will also change here as well. Okay. Also, I'm setting up some validation here, making sure that the SID is positive and that the graduation year is greater than the year that the school was founded. Okay, so I'm not accepting any graduation year before the school was founded. Okay, so it's here's some more details on the cascade checks that we can set it to null, set to default, or no action, meaning don't do it, reject the change, and some validation checks that we can do.